Welcome to our laboratory. I am Valery Levitas. I am Distinguished and Chair Professor here at Department of Aerospace Engineering. This on the left is Dr. Sorki Sudhas, Research Associate. On the right is Dr. Marinmei Zahu, Postdoctoral Research Associate. They are experimentalists. They are around this lab and are responsible for all experiments in our group. And our field of research is high pressure science and technology. Someone has idea what is high pressure? Where it is? By the way, don't hesitate to ask question, interrupt me, ask question. If you know what to say, just say. If not, if someone knows what high pressure is, what possible.
So when he says high pressure, what do you think of?
Yeah.
What does that make you
Isn't
think
that
of?
like the forces that the aircraft in question handles or gets exposed to?
It's also they're exposed to high pressure also. Yeah. So first, we are surrounded by air, and air pushes our body. That means produces pressure. And magnitude of this pressure is 1 atmosphere. But we adjust it, we don't feel it, right? Our body, vessels, everything are adjusted, we don't feel. How to feel high pressure? Dive, right? If you're deep in pool or in ocean, you feel like water squeezes you, right? If you're at the depth of 1 meter, this is extra pressure due to water is just 1/10 of atmosphere, right? But you already feel it. Few meters, you feel significant pressure. It's difficult to sustain. 10 meters, this is 1 atmosphere. So that is what we adjusted to, but this is extra 1 atmosphere on the top of air, right? The deepest place in ocean is more than 10 kilometers. And 10 kilometers pressure is 1,000 atmosphere. So you got idea of magnitude. And this is huge. It squashes submarine if they are not specifically designed. And we are here interested in pressure from 100,000 atmospheres to million atmospheres. So it's 100 to 1,000 times more than at the deepest point in ocean. Right? So, 2 questions. How to produce such high pressure? Second, why we need this pressure? Right? First, each high pressure laboratory has a diamond anvil cell. So what is the strongest material? Diamond, right? That is why diamond is not only jewelry, it's working material. We use it as anvils. So these are 2. You will see all this alive. All these diamonds, this diamond anvil cell, 2 diamonds, and this is sample. Thin film is our sample, right? And if sample material is weak or it's powder, then we use gasket. So it's made of solid materials like stainless steel. Drill hole, you will see this hole, and place sample in the hole. And then you place sample within gasket or without gasket between these 2 diamonds and squeeze it. And that is how you can produce very high pressure, as I told you. Why, how it works? Well, we apply force to large area, and force pressure is force divided by area, right? And sample is subjected to action of small area. And differences area could be by factor of 1,000. So that is how we multiply applied pressure by factor of 1,000. And this is main principle. So that is how high pressure is produced. Also, diamond is transparent material. You can see everything in microscope, optically, what's going on during compression at the surface. But most important, using modern technologies, you can probe what's going on within sample. Main technology is X-ray diffraction. without going in detail, it measures distance between atoms and how it changes during compression. And also some defects, grain structure, various things. And for this experiment, you need very powerful sources of X-ray. University cannot afford this. There are special governmental facilities, which are called synchrotron radiation facilities. Closest one, which we use, is at Argonne National Laboratory near Chicago. So they have all measurement, controlling equipment, staff who knows how to handle this. Diamond angle cell with sample, like here, is prepared here, and then these two fellows go, staff helps them to fix on their stage, connect all equipment, and then it's 48 hours of continuous study, because it works day and night, because it's expensive. These are expensive, unique facilities. And that is where a lot of all entire information experimental is obtained, and then at years of post-processing, of extracting useful information from what is measured, right? So that is how it works to produce and to study what's going on at high pressure. Why we need high pressure? Many applications. One of them is to produce new materials, high pressure phases. So, and best example is diamond, man-made diamond. Okay, so carbon exists in two phases. One is diamond, this strongest, beautiful material. Another is graphite, what you have in a pencil, big gray material, right? This is the same material, it's carbon, but it's two different phases. What does it mean, phases? What distinguishes them? They have different mutual location of atoms. They are located completely different in graphite and diamond. And under some action, you cannot believe it, but this graphite can be transformed to diamond. That is what is called phase transformation. So phase transformation, graphite to diamond, and this is basis for obtaining diamond. I am sure you know and can tell me other good examples of phase transformations. Can you? You know.
Really?
Yeah, absolutely you know. You do this each day.
Water and ice.
Great example. Water and ice. If you cool water, liquid transforms to solid. If you heat solid, it's transformed to ice. What else? If you heat water.
Water.
So it's phase transformation from liquid to gas, and vice versa during cooling. So this is an example of phase transformation you are familiar with. This is maybe a little bit new for you, but point is, it's within solid, and one crystal structure, so some mutual location of atoms transforms to another, and everything is changes. This transforms to this. Okay. So what you need to transform graphite to diamond, you need to apply in industry. This is already industrial technology since 1960. You need to apply pressure of 50,000 atmospheres. Remember, the deepest point in ocean is 1,000 atmosphere. This is 50 times larger. You need temperature of 1500 Kelvin. And you need to add metal which serves as catalyst. It means it accelerates phase transformation. That is how it works in industry for a long time. Well, if there is technology, researchers, engineer wants to improve. What would be global improvement? First, to do this at room temperature. Then we don't need equipment for heating, we don't spend energy for heating, and also at high temperature tool which squeezes graphite, it breaks easy. And this adds significant cost to diamond. So, okay, first to do this at room temperature. If you do this at room temperature, catalyst does not work in any case. It's good to remove it. And then it takes space. First, it takes space. Second, after this compression and heating, metal melts, and then it solidifies. Diamond is covered by metal, so you need to remove it, and there are special chemical technologies, and they are not good for environment. So that is why it's good to eliminate catalyst also. And also it would be good to reduce pressure. The lower pressure, the cheaper diamond, because you can, tool can do many more cycles of compressing graphite, different portions of graphite. Okay, so people try, they succeeded, but pressure which they needed, if it's at room temperature without catalyst, was 700,000 atmospheres. In industry it's 50,000, this is 700,000. It's more than 10 times, it's no go. No, right? And that is where we come into play. So what we are doing differently here from others. After compression with two anvils, we twist one with respect to another, producing torsion. So now this is new device, it's called rotational diamond anvil cell. I brought this device to US in 1999 from my former lab in Kiev, Ukraine, and this was beginning of corresponding study in the United States. And what this rotation of anvil produces? It produces large plastic shear. I will explain you what does it mean shear, what does it mean plastic. So, this is compression, and I push hard, but you don't see any deformation. But if we produce shear, for example, this is shear. One layer is shifted with respect to another. You see very large deformations, right? And large deformation, and with small force. And large deformations produce a lot of changes in material structure, and they prepare structure for phase transformation, help for phase transformation. Well, if you want to imagine shear during torsion, it's the same. So one layer is twisted with respect to another. Okay, so and you can twist it several times, so it will be a huge deformation. It's not visible as well as good as what I show you here, but it's the same large deformation. Now, what is plastic? If you consider this, apply force, remove force, it gets back. This is elastic deformation. It's reversible. That is what we use in springs, right? What is here? You produce deformation, remove force, it stays. That is what we call plastic or residual. And you know many examples of plastic deformation in industry. Forging, rolling, right? All where you need to change shape, and this shape remains, right? It does not go back, like for booming, right? This is examples of plastic deformation. So now you know that we apply large plastic shear, like this or like this. And with large plastic shear, what we are able to do, we were able to obtain diamond from graphite without temperature, without catalyst, and at pressure as low as 7,000 atmospheres. So instead of 700,000, it's 700 times lower. This was revolutionary. It could lead to new technology of diamond synthesis. Now it's just proof of concept. A lot to do to get to technology, but if there is proof of concept, it should sooner or later with technologies. Did others try to do this? Yes. First, in last century, Professor Bridgman from Harvard, he was founder of high pressure research, and that is for this works he received Nobel Prize. He tried to get diamond by sharing, he did not succeed. Many others did not succeed. There were groups which succeeded, but it was at pressure of 200,000. So instead of 7, 200,000, which is for industry, it's not no go, too high pressure. So, okay, why we were able to do what others could not do? Mostly because we are also developing theory. So based on theory, we now have knowledge how this plastic shear changes microstructure, how it affects phase transformation, not only phase transformation, also chemical reactions. And so we know how to control, how to prepare initial sample to get maximum reduction. And that is why we are having leading position in the world in this field now and can do what other cannot. It's both very sophisticated theoretically and very sophisticated experimentally. So such experience as these two fellows have, maybe few others in the world who have, and all of them who came from this lab. They are working at different places now, and others don't have such high level of experimental expertise, and practically no one is doing theory. That is why we live here. Also, plastic shear not only reduces phase transformation pressure, but also can lead to new phases which could not be obtained under hydrostatic compression. So it's way to produce, to search for new materials. Also, plastic strain accelerates drastically. It can be sometimes million times accelerates phase transformation and also chemical reactions. And in many cases, you compress material, you get high pressure phase, then you reduce pressure, and this phase goes back. It's interesting from scientific point of view, but no practical use, because it does not exist at normal conditions. So plastic straining also, in many cases, can arrest high pressure phases and make them available for usage at normal pressure, like diamond. Okay, and we are working with many other materials and for many other applications. For example, electronic materials, silicon and germanium. Recently, Dr. Isudhas reduced phase transformation pressure from semiconducting to metallic phase of silicon by a factor of 54. It's huge. And Dr. Zahu did very similar work with similar reduction for similar phase transition in germanium. This is another important electronic material, right? We produced phase transformation to super hard boron nitride. This is second strongest material after diamond. It's very similar phase transition like graphite to diamond. From graphite-like boron nitride to very strong diamond type cubic boron nitride. Also, we work with rocks, earth materials. And what with olivine, for example, we found by shear phase transformation in olivine and proved that this phase transition may be source of earthquakes. So they lead to earthquakes deep in the earth. And geophysicists are very interested to understanding of how earthquake initiates. If you know how it initiates, you may think of mitigation of damage, right? We did phase transition, studied phase transition in various metals, zirconium, titanium, iron alloys, how to improve properties based on this material treatment. And there are various applications. So I mentioned you material synthesis and geophysical applications. Pressure in Earth is huge. High pressure, high temperature, and you cannot get to these places deep in the Earth, right? So theoretician calculated pressure and temperature at each position of Earth, at each radius, and we can reproduce this pressure in the lab. Now we can do not only pressure, but also shear, which is important. Then also friction. Friction is shear. This is one is sheared like here. It's sheared one way with respect to another. And if strong material and high load, this is the same, compression and shear. So we can determine loss of friction. And if friction causes wear. So it's also we can determine loss of wear. Then all surface treatment, polishing, cutting, this is shear. You remove material by shear, like here. You remove material, right? Layer by layer. And if material is strong, like ceramics or semiconductors, you need large force. That means you have large pressure and shear. So we can understand processes during surface processes during processing of material surface. Then military application. For example, when projectile penetrates into target, it's high pressure, high temperature, but also large shear. And if everyone studies at high pressure and temperature, we added shear, and that is why Army is very interested in our work and support us for decade, more than decade. What else? Probably these are main applications. And recently we started experiments with dynamic rotation diameters. All what I told you before, rotation is quite slow. So it's like one rotation per hour, very slow. Last experiments was with 4,000 rotation per minute, not per hour, but per minute. This opens completely new field of research, not only plastic shear effect, but shear rate, how fast you apply shear, right? And this is important for dynamic processes like all military applications or even high-speed polishing. You processes occur at very high strain rate, and now we can reproduce this strain rate. So it's growing field, it's future in high-pressure research and technologies, and we are happy to initiate this field and be forefront of this. And now, do you have questions to me? Yep.
Concerning the pressure, why do you want it to achieve the same goal as like 200,000 atmosphere compared to why do you want to go all the way down to 7,000?
Because it's cheaper.
Okay.
It's cheaper. You know, for example, such pressure we can obtain a PLC sample.
Mm-hmm.
It's comparable with hair because it's very high pressure. In industry, so for example, sample which is treated for industrial diamond synthesis, it has diameter 40 millimeters, 60 millimeters. You need huge presses for this, huge tool, dies, right? And all this surrounding equipment. It's very expensive, very expensive. If you can, you know, I remember I used to work at the Institute for Super Hard Materials in Kiev, Ukrainian Academy of Sciences. When one fellow did a lot of study and he reduced the pressure from 40 for diamond synthesis, from 45 to 44,000 atmospheres. It was a big deal because tool can stay longer. And cost of diamond is mostly cost of tool. At least it was back in Ukraine. I don't know exactly. Here probably workers get more, so it's salary plays important role, right? But yeah, and we reduce from by factor of 100, right? With current with 50 versus 7, right? Like more than 10 times, but without temperature, without catalyst. So this is very important goal. Very good question, yeah. Yeah?
Use another material to apply the pressure like diamond.
In industry it's not diamond, because diamond is small. In industry it's hard ceramics. This is so-called tungsten carbide with cobalt alloy. Or stainless steel. Special, highly alloyed stainless steel. Yes, very good question. Yep.
For the application, can you use other materials like such as metals, so you can create like a new strain that can handle high stress?
For metals, you can metals have phase transformations also. Which metals which we study, they have phase transformation. So you can produce high pressure phase, or you can partially transform, produce composite, and you can refine grain with this method. So it's economic way to refine grain, which is to produce nanostructured materials. Guys, in contrast to previous group, you have very good questions. They had 0 questions. Okay, yeah, go ahead.
What was one project for you that was really difficult and that you were able to achieve, that you thought was like really important to you?
Everything is difficult. Us guys, everything is difficult. You know, to prepare one experiment, just to prepare, not to perform, they spent 1 month for one, because you know, alignment, this is small size, right? And precision which we need is much well higher than what usual people do who just compress. Now, especially with high strain rate. Previously, they spent few days to align, to prepare a cell for experiment. Now it's 1 month, if they are lucky. And conceptually, each time we get surprises. You expect something, you get something from you expect, but you get something completely different. We change your mind. You don't know what it is. How you know you believe that you have clear picture what's going on, right? And then you get something which is completely contradictory or does not fit to this picture. You need to imagine something new each time. Yeah.
How far does that set you back? Whenever you do something and it just completely shatters what you thought, does that take a long time to figure out like what to do from there?
You know, I can tell you. Now we are writing paper on IRA. These results were obtained probably 8 and 7 years ago. I could not explain them. It's complete nonsense. Now, when we learn from other materials, got experience, deepen our theory, now we start understanding what's going on. But sometimes you obtain something great. If you can explain this, it takes 1 or 2 years to publish in high level journal paper. Right, so, yep.
So most of your research is done in Chicago?
Yes, all actual measurements are done in Chicago.
But you start off with the idea here.
Yeah, you cannot think a lot in Chicago because you have 48 hours of continuous work.
So
Right.
do you have
All
to,
ideas, all preparation. When you apply for experiments, you need to win beam time to get to there. This is competitive also, right? You need to describe a clear plan, what you will do, why, what you expect to get. And then you compete with other proposals. When you get, you already, everything is prepared here, right? And tested to some extent. So there is Raman equipment here. This is, it can tell you something about phase transformation. It's very important for study. This is a separate field, Raman study. But for us, if you're interested in phase transition, it can detect phase transition in many materials. It does not give as much detail as X-ray, but at least preliminary work can be done here. Yeah?
And keep in mind, this is all a scientific process, right? And I was interested when some of you were talking about results, but Doc said, just because it's not what you expect doesn't mean that it's not a valuable finding, right?
Oh, this is even more valuable if you get what you expect.
Right.
Because then you need to do something new. Current state of the art is challenged. So, when you get something which you cannot explain, you have two-side feeling. First, oh God, again. But you realize that this is future. That is what you will do in future, and you will get definitely new, something new. There is no way back. Okay, guys, now if you want really to see something, it's time for fellows to show you, right? And you can ask question meanwhile. Thank you. Go ahead.